Okay, and with that, maybe I'll turn it over to Manar.
Okay, thank you, Jeff. So just let me share my screen for the presentation. So hi everyone, I am Manar Abdulati and I am an ADA engineer at eFabless. And today I will give you an overview of the Caravel chip and how to use it to start designing your user project for the eFabless shuttle programs. And I will also cover the example user project, which is called the Caravel user project that eFabless published for as a template for digital user projects. So Caravel is the standard SoC harness for the eFabless shuttle programs. So whether you are on the Open MPW shuttle or the Chip Ignite shuttle, you will need to use Caravel as a carrier for your user project. So all the components on the Caravel chip are pre-designed and they are the same for all the user projects. So around the user project area here, we have three main components. The first one is the management area, which contains a RISC-V processor. And we also have a storage area, which contains two SRAM blocks of memory. And we have a management protect buffers to isolate any connection between the management area and the user project area. And as you can see here, everything in the chip is pushed down to the bottom to try to make as much as empty space as possible for the user project area. The chip pad frame is also pre-planned, which means that you get a fixed number of GPIO pins, and you also get a fixed number of power domains. So the first main hardware resource in Caravel is the management area, and it contains a PicoRV32 processor, and it also contains a number of digital peripherals like the SPI master, the flash controller, UART, counter and timers, and it also contains a digital PLL clock, which provides an option to multiply the external clock coming from the clock pad by a factor of 2. And the processor also has the option to bypass the PLL completely and use the external clock as is without any multiplication. The management area also contains a large number of GPIOs, which are shared between the management area processor and the user project area. There is also a flip-flop based memory in the management area. It is generated by the DFFRAM memory compiler, and it has a size of 1K. And there is also a secondary memory, an SRAM memory, and this SRAM resides in the storage area. So the storage area contains an auxiliary space for the management area. It is currently it is only accessible by the management area, and it hosts two 1K SRAM blocks, and these blocks were generated by the OpenRAM memory compiler. So the decision of having a pre-planned processor in Caravel was made to simplify a number of tasks for the user projects, one of which is configuring the GPIO pads. So the task of configuring the GPIO pads is very complex, and it involves a large number of control signals. And this task is mainly done by the management area processor. So the user project can easily configure the GPIO pads to be an input or an output or a bidirectional pad by running a firmware on the management area processor. So as I said, the chip pad frame is fixed. So you get a fix is pre-planned and pre-designed for all the shuttle chips. So you get a fixed number of GPIO pads, which is 38 GPIO pads. And every pad is shared between the user project area and the management area. And every pad is multiplexed between the two, and there is a control signal that controls whether this pad is under the control of the user project area or under the control of the management area. And the user project space has a complete authority of enabling or disabling this control signal. So the user project can leverage the pad if it needs to, or it can leave it under the management area control. And because we have a large number of pads, 38 GPIO pads, and because each pad contains a large number of control signals, you will find that each GPIO control block contains a shift register, and this is to load the configuration for the pad serially and to reduce the chip routing resources between the management area and the pad frame. So if we place all the GPIO control blocks next to each other, they will form one large serial shift register. The management area also provides another utility for the user space, which is the logic analyzer probes. So you get access to 128 full duplex logic analyzer lines. So in practice, you have 128 input lines and 128 output lines. And you also get access to the out enable signal. The typical use case of the logic analyzer probes is that you can monitor certain signals in the user project area through the management area processor. And you can also use them as general purpose IOs. So you can set certain IOs in the user project space or read from them using the management area processor. The third utility that comes from the management area is the wishbone port. So the main bus in the management area SoC is a wishbone bus. So all the peripherals are designed around the wishbone. And the management processor exposes a wishbone port that can be connected directly, that is connected directly to the user project space. So you get access to these signals, the wishbone clock, the wishbone reset, strobe signal, which acts as a select signal for the wishbone client in the user project area, a cycle signal, which indicates the start of a wishbone transaction, a write enable signal, and the select enable, which selects a byte out of a 32-bit word, and the data and address lines, and also an ACK signal, an acknowledgement signal, which indicates the end of a wishbone transaction. So using this wishbone port, you can build a wishbone client in your user project space, and you can communicate to this client using the management area processor. There are a number of additional utilities that are provided in the user project space. The first one is that you get access to a secondary programmable clock called the user clock 2. So the user project area gets access to two clocks. The first one is the wishbone clock, which is the main clock that the management area processor operates on. And a secondary clock called user clock 2, which comes from an independent integer divisor from the PLL. And you also have the option to bypass the PLL and use the external clock coming from the clock pad as is. Another additional utility is that you get access to 3 interrupt lines from the user space. So you can interrupt the PQRV32 CPU from the user project area. And you will need to enable the interrupt line through the management SoC firmware. So in summary, the user project area gets access to 38 general purpose I/O ports. These ports are simplified as an input, output, and output table. And you also get access to 128 logic analyzer probes, which are full duplex. And you get access to a wishbone port connected to the management processor main bus. For the power domains, you get 4 power domains. 2 of them are 1.8 voltage, and the other 2 are 3.3 voltage. And in the picture here, this is the empty golden wrapper, the user project wrapper in Caravel, and it has an area of around 10 millimeters. So you need to design your user project to fit within this space. Your user project, the golden user project wrapper has a fixed pin location. So the south-facing pins are the pins which are connected to the management area, which are the wishbone, logic analyzer, and IRQ pins. The rest of the edges contain the GPIO pins, which are the input, output, and output enable. The blue and yellow lines here are the core rings. And the user project wrapper, as I said, gets access to 4 power domains. So we have a core ring for each power domain here. And those are also fixed. So you need to have the same core rings in your user project wrapper. So the user project area, the integration is done as follows. Caravel is designed with modularity in mind. So you need to only provide the user project wrapper GDS file, along with the other design files like the Verilog RTL and gate level and the test benches. And then as part of the tape-out process, the user project wrapper GDS file is integrated into Caravel with an empty user space. And to make sure that this integration process goes seamlessly without having any issues, you have to follow a number of requirements. So these requirements are as follows. First, your top module name for the GDS file must be a user project wrapper. And you must adhere to the pin location and pin sizes that are specified by the golden user project wrapper. This is mainly because all the chip routing is pre-planned before integrating your user project wrapper into Caravel. So if you change the pin location or the pin size, you will risk having DRC and LVS issues in your design. You will also need to have the same core rings and the same straps widths as the golden wrapper. And this is also because the power routing is pre-planned with the golden wrapper in place. However, you can change the following. You can change the horizontal PDN stripe or the vertical pitch of the PDN. And you're also free to change the PDN stripes offset, whether it is horizontal or vertical. So how to start your user project? This is mainly for the digital design flow. We published a template user project for digital design called the Caravel user project, and you can find it under this URL. And the repo contains the design files for an example user project, such as Verilog test benches and layout files such as GDS and def and lef. And the repo also has a top-level make file which automates the use of various open source tools like OpenLane or using the simulation, the RISC-V toolchain simulation, or using the eFabless MPW pre-check. And as a designer, or as a Caravel user, you will need to start by using the Caravel user project. So you will need to adhere to the same directory structure given in the template project. The first highlight about the structure is that you need to have the Caravel repo itself as a submodule in your user project. And this is mainly because you will need Caravel in your design iteration, like for example, in running the full chip simulation or getting the OpenLane configuration for the pin location and pin sizes. So you will need to have the Caravel repo submodules in your user project. And because we know that the Caravel repo size is huge and it might be cumbersome for some users to clone the whole repo, we provide a lightweight version of Caravel called Caravel Lite. And it is another repo. It is basically a mirror for the main Caravel repo, but without the large files like the full layout of Caravel. So it only has user like the files that you need as a user. So it has the Verilog RTL for Caravel and Verilog gate level to run full chip simulation. It has the golden wrapper configurations, but it doesn't have the like the large files like the GDS files for the Caravel chip. You will also need to have a Verilog directory which contains the RTL and gate level for your design. You will need to have the GDS directory, the def and lef. And if you're using Magic or OpenLane, you will need to have the mag and the maglev directories. And if you're submitting for the open source shuttle, you need to have a license file. So for the example user project, it comes with a very simple example. It is basically a 32-bit count register. We purposely made it simple to showcase how to use the various management area interfaces. So the counter makes use of the GPIO pads. It uses them as an output pins to display the current count value. And it also makes use of the wishbone port to read or write from the count register. And it also makes use of the logic analyzer probes to also read or write from the count register. And the logic analyzer probes are also used to supply a secondary clock for the count register. So it either uses the wishbone clock or the secondary clock based on the select line here, which is provided also by the logic analyzer. So looking at the Verilog files for the example project, you will find that the top module is named user project wrapper, which is a requirement to have. You need to have your top module named user project wrapper. And for the module header, you will find that the pins here specify like match the user project area interface to the management area. So we have the power pins for the 4 power domains first, and they are guarded by the use power pins macro, and this is an OpenLane requirement. So if you're planning to use OpenLane, you will need to have all your power pins and power connections guarded by the use power pins macro. And then you have the wishbone port, and then you have the logic analyzer pins, the input and output enable, and you have the GPIO pins, and then you have the secondary clock and the 3 IRQ lines. So every user project submitted to the shuttle program will need to adhere to the same module header given here. So you need to have the same pin declarations, the same pin types, the same bus widths. So you need to have the same module header as here. And in the example project, we have another module inside the user project wrapper, which is called the user proj example. And this is the module which contains the count logic and its connection to the wishbone and logic analyzer and the IO pads. So after you're done writing the Verilog code for your design, it is very important that you run full chip simulation with Caravel to make sure that your design works within the context of Caravel. And also after you're done with hardening your design, and if you have your gate level netlist ready, you will also need to run the gate level simulation. And this is to make sure that when your design is placed in side Caravel, it will work correctly. So the example project provides a set of scripts to run the user project example and the user project wrapper through OpenLane. And the design approach followed here is that we first hardened the user project example as a separate macro, and then we placed it in the user project wrapper without having any standard cells on the top level. So this is one of the possible design approaches that you can follow, which is placing your macro, your hardened macro in the wrapper. Like, for example, the Pi5 project here, which we had in the first MPW shuttle. So all the design logic is encapsulated inside this macro. And on the user project wrapper top level, we don't have any standard cells. Another design approach is that you could flatten your design with the wrapper itself. So you don't have any macros inside, you just have standard cells on the top level of the wrapper. This was not a very popular option because I didn't find any one of the shuttle projects who did this, but it is a valid option if you need to. The third option is a mix between the first and the second, which is that you could have a macros inside the user project wrapper plus some standard cells on the top level. And an example of this is the Caravel Ibex project, which we had for the first MPW shuttle. So after you're done hardening your design, you will need to run it through the Open MPW pre-check. And the Open MPW pre-check, it is a sign-off tool to confirm that your submission is valid for the shuttle. It is developed by eFabless. And you have the option of running the tool offline, locally on your machine, or you can run it on the platform, on the efabless.com platform. And the main purpose of the pre-check is to make sure that your design is ready for the shuttle submission. So it runs a number of checks. One of them is the license check. So if you're submitting for an open MPW shuttle, you will need to have a valid open source license. And the second check is the consistency check, which makes sure that your design adheres to the golden wrapper requirements in terms of pins and power. And the third check is the DRC check, which makes sure that your design doesn't have any DRC error. And the fourth check is an exclusive OR check. So in this check, your GDS layout is XOR'd against the golden wrapper layout. And if there are any differences between the two, it will be flagged as an error. And this is to confirm that your user project wrapper adheres to the golden wrapper in terms of the pin placement, pin size, and the coreings. So if you change any of those, for example, if you change the pin location of one of the pins, it will be flagged by the XOR check. So these are the set of tools that you will need to jumpstart your design. The first one is a prerequisite, which is Docker. So most of the open source tools that we work with are installed using Docker. So you will need to make sure that you have Docker in your environment. The second is the Skywater PDK. And the top-level makefile in Caravel and Caravel user project provides the makefile target for installing the Skywater PDK using the Open PDKs. And you will also need to have the RISC-V toolchain and iVerilog and GTK Wave installed. This is to run the simulation with the full chip simulation with Caravel. And we also provide a Dockerized version for these, so you don't need to worry about installing them locally on your machine. If you're planning to use an open source digital design flow, you'll need to have OpenLane installed. You can also elect to use a commercial flow if you need to. And you will need to have the MPW pre-check tool to sign off on your design and to make sure that your design is ready for the shuttle submission. And it is also recommended that you have K-Layout installed. It is a layout viewer and editor, so you can use it to view your design files. And you can also have Magic and Engine installed, Magic for running DRC and Engine for running LVS. So now I think it is time to show you like a quick demo of how to make use of the Caravel user project and how to use it to run the full chip simulation, and how to use it to harden the design using OpenLane, and how to run the pre-check. So here I have the Caravel user project, and the Caravel user project, it comes with an empty submodule. So the first thing that you will need to do is that you will need to initialize the Caravel submodule. And to do so, you will need to run make install. And this will start initializing Caravel Lite. It will fetch Caravel Lite, and it will initialize it as a submodule under your Caravel user project. So while this is going, I will just leave this running till it finishes, and I will go over the PDK installation. So the next step after submodule in Caravel, you will need to install the Sculptor PDK. And to do so, you first need to export PDK root, and you will need to the absolute path where you need the PDK. So here I will put it under open PDKs, and then you will run make PDK. Just make PDK. I already have this installed, so I won't run it. So, but like you to run make PDK and hardening design using OpenLane. It's got Caravel Lite, and here you can see that you have some wrappers. For the digital flow, you are mainly interested in the user project wrapper empty, which is the golden wrapper for the digital wrapper. And you also have the left view for the golden wrappers, the Mac view. And you have the Verilog RTL and gate level for the full Caravel chip. And you will also here have the OpenLane configuration. These OpenLane configuration are fixed configurations for the user project. So you cannot change any of these sections. These specify the pin locations, the pin order, and the pin size. So, and the core ring as well. So you will need to keep, you cannot change any of those configurations. So now the next step is you will need to run the full chip simulation to make sure that your design works within the context of Caravel. So you will need to grab, you need to have the RISC-V toolchain installed, and you need to have iVerilog installed. And if you don't want to install them locally, we provide a Dockerized version for them. And to grab this Docker image, you can type make sim in, and this will start pulling the DV setup that we have. So this Docker image again has the RISC-V toolchain and iVerilog installed. And then after this, you will be ready to run any of the test benches. So the example project comes with 5 test benches. And under each test bench, you'll find the test bench module and a .c code. And this .c code contains the firmware that runs on the management area processor. So here you can see that it is configuring the lower 8 I/O pins as output pins, and it's also configuring them to be used by the user project area. And then it applies the configuration by initiating the serial transfers through the GPIO control block data register. So if you want to run any of the test benches under the Verilog DB directory, you will need to type make verify dash and then the test bench name. So here, for example, I will run the IO ports test bench, and this will start running the test bench. This will take a couple of minutes to finish, so I will leave it running. But the expected output is that you will get a passed statement indicating that the test bench simulation passed. The second option about running the simulation is that you can run the simulation with the gate level. And to do so, you will need to set sem to gate level by saying sem equal gate level, and then typing make verify wishbone port, for example. So here we will run the gate level simulation for the wishbone port test bench. And if you type, and this will take around 5 minutes to finish, so I will leave it running here. And I will go over to hardening the design using OpenLane. So first, you will need to get OpenLane installed in your machine, and to do so, you will need to export the OpenLane root, and then you will need to set it to the absolute path to where you want to install OpenLane. So in this case, I want to install it to efabless/OpenLane, and then you will simply type make OpenLane. I already have it installed, so I won't run this because it will take a long amount of time. But after you have OpenLane installed, you will also need to export the PDK root before running the OpenLane hardening step. And then to harden any of the design macros. So here, for example, in the template project, we have two macros. We have the user project example, and we have the user project wrapper. And under each macro folder, we have a configuration.tcl, which defines the flow configuration for OpenLane. What I want to highlight here is that in the user project wrapper configuration, it is using the fixed wrapper configs from the Caravel submodule. So you will need to always source the fixed configurations from the Caravel repo, and you will need to leave the fixed wrapper configs unchanged because this is what specifies the pin location and pin size and the core ring. And also you are free to change any of the flow configurations defined here in the config.tcl itself. So you can change the clock period or any of the flow control here if you need to. So to harden any one of these macros, you will need to simply type make and then the macro name, which is here, for example, it will be a user proj example. So this ended up with an error because I didn't export the correct PDK root. So I need to fix this. So then the macro name will start running OpenLane on the given macro name. So here it will take also a couple of minutes, so I will leave it running. And I will move on to installing and running the MPW pre-check. So like the other tools, to install the pre-check, you'll need to first export the pre-check route, which is, in this case, I will want to install it here. And I already have it installed, so I will not run the installation step, but the installation step for the pre-check is make pre-check. So this will install the pre-check, pull the pre-check Docker image, and install it in the given pre-check route. And to run the pre-check on this user project, I will need to type make run pre-check. And this will start running the different pre-check sub-checks. Like here, for example, it is running the license check. And then it goes to the XOR check. One check that is expected to fail on the template projects is the default content check. And this because this check makes sure that your user project has modified the template project files. So it is expected to fail on the template project since the GDS files are unchanged. But it should pass on your user project if you modified the GDS layouts here. So that is pretty much for the Caravel and digital user project flows. There is another twin sister of Caravel called Caravan, which is a modified version of Caravel to better support the analog project. It is very similar to Caravel in the sense that it has the same hardware resources. So it contains the same management area, the same management protect buffers, and the same storage area. The only difference between the two is the chip path frame and the user wrapper. So in the analog, it is called user analog project wrapper. And also have a template project for the analog flow called Caravel user project analog. So if you're interested for analog, check the template project and check the specifications for Caravan. That's pretty much it for my presentation. Thank you so much for listening, and I look forward to your questions.
Excellent. Hey, thanks, Manar. That was great.
Thanks.
So yeah, we should open it up to questions at this point. So go ahead and ask your questions at KI.
Okay. One question I have about macro that you harden in your Caravel flow. So when you generate basically GDS file of your macro, so in that you also have to define your PDN network. I mean power rings.
Yes, you need to define the powering. Like, are you planning to use OpenLane or a commercial flow?
OpenLane.
Yeah, so in OpenLane, in the fixed wrapper config.tcl, you will find the PDN core ring configurations here. So starting from like all of these configurations, configure the core ring. So for example, it configures the width to be 3, the vertical width, the horizontal width, the offset, the vertical spacing, and the PDN network is planned within the OpenLane flow.
But to clarify, Manar, that's for the user project wrapper, right?
Yeah.
I think his question was with respect to macro within the user project wrapper.
Yes, my question was relevant to macro, not the user project.
Yeah, so for the macro itself, you will also need to plan the PDN. Like OpenLane has a default PDN generation, which is that it plans the PDN power on metal 4 and metal 5. If you set this variable design score to 1, if you set it to 0, it will be planned on metal 4 only, so you can place it on a top level macro. I can direct you to the PDN configuration documentation on OpenLane, because there is more to it than this.
Sure. Thank you.
Yeah, another attendee has a question regarding analog IOs in the chat. I believe he has typed, can you briefly tell about analog IO on Caravel?
I can't speak of Caravan. Like the guy to ask here is Tim Edwards, because he's the one who designed Caravan. You can ask on the Slack community on the Skywater PDK. There's a channel called Caravan, and you can direct your questions to him.
Yeah, I mean, I think at a very high level, Manar, you showed the outline of it, and the main difference, as I understand it, is the pads. There's a set of pads at the top that are been modified to be basically bare pads that have no ESD protection, and that any ESD, really to enable support for high speed or high voltage requirements that you might have for your project, and that any circuitry that you would need to implement for ESD, you have to implement yourself within your user project wrapper, user project design. So, but Tim is the right resource for that. There's more information, I think, on that repo that Manar showed, and then you could also post questions to him. I believe there's actually a channel on analog design specifically in the Slack, or Caravan specifically.
Yeah, there is one on Caravan.
Yep. Yeah, there's a Caravan channel, so that's probably the best place to post questions, or even find maybe some answers that you might already have that might already be posted. Okay, other questions? Okay.
I have a question. You also mentioned that the flow can be continued using the commercial tools. Which commercial tools are supported on the Skywater PDK as of now?
So there are users that are using commercial tools, a variety of different commercial tools. That we don't have a specific constraints or support specifically enabled for any one particular tool, but there are. I do know that a number of tools are being used or have been used. I know there's been projects that have used Cadence. I don't know about other, I think, and I don't know about other tools that I've seen beyond that, but there are, the PDK itself provides kind of generic, or provides compatible file or views of cells in like LEF and DEF formats that can be used with a variety of commercial tools. And in terms of specifics, questions you might have in terms of how to configure that or work with those, I would suggest joining the Slack channel and then looking for that specific tool in the or channel specifically for that tool, where you can post questions to other community members who have used the tools or have already gone through that. Okay, any other questions? Oh, okay. So, Kashif, is there, in terms of just to have a question about, potential projects that might be, closer to completion or maybe ready to consider, like an upcoming shuttle that we have that's going to be taping out in November? I don't know.
Yes, actually, today we were supposed to do meeting today morning, but somehow we could not manage to do. So probably I will let you know. I mean, I will connect you with the community by tomorrow.
All right.
Probably.
Awesome.
Yeah. So I will summarize their current project that's going on in Pakistan.
Great.
Yeah.
Okay. All right. Great. So
Okay. I think we can wind up now. If
right. Yep. Yeah, I just was going to make it a heads up that there is a I think you're going to talk about this separately, right? But there is a shuttle that we have going out in November, and so we are
yes.
considering projects that we're looking to see if there's any projects that may be ready in time for that shuttle.
Sure. I will let you know.
Okay.
I will let you know. Mm-hmm.
Okay. All right. Great. Well then.
Okay. Thank you so much, Jeff and Manar, for giving time.
Yeah, you're welcome.
Thank you.
Thank you.
Okay.
Thank you, everyone. We'll go ahead and end the meeting now. Thanks.